Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. The supply chain for artificial intelligence is the full network of ingredients and hands-offs that bring a system from an idea to a running service. Think of it as every upstream input and downstream output that touches your model. Datasets, labeling workflows, model checkpoints, libraries, build tools, containers, and the services that surround inference. Unlike a single application binary, an AI system is assembled from artifacts that evolve at different cadences and are often sourced from communities you do not control. Each step introduces assumptions and trust decisions. Knowing this chain matters because reliability, safety, and compliance are only as strong as the weakest link. If data collection is sloppy, labeling can't fix it. If a base model is tainted, fine-tuning can amplify the problem. A disciplined view of the supply chain lets you see where risk enters, how it propagates, and which controls must be applied to keep the system trustworthy. When we say upstream and downstream dependencies, we're describing direction and influence. Upstream is anything that feeds your system. Raw data, annotations, third-party model weights, open-source libraries, and the compilers or CUDA stacks that make training possible. Downstream is what your system feeds: embedding stores, applications, agents, plugins, and customer experiences. Change typically flows downstream. An upstream dataset correction ripples into retraining and new behaviors. Yet feedback also travels upstream when incidents or metrics demand remediation. Visualize a river delta. Tributaries merge, sediment moves, and eddies form where flows interact. A library bump in a pre-processing step can alter tokenization. A base model upgrade can shift instruction following style. A minor driver patch can change numerical stability. Mapping these flows helps you predict blast radius and design rollback paths. 3 upstream pillars deserve clear definitions: datasets, models, and libraries. Datasets are structured collections of examples-text, images, audio, labels, and metadata assembled through scraping, partnerships, or human annotation. They encode both knowledge and bias, and their provenance determines what you're legally and ethically allowed to do. Models are parameterized functions, usually neural networks, trained on datasets to learn representations and behaviors. Pre-trained models are checkpoints produced elsewhere that you adopt as foundations. Libraries are the scaffolding frameworks like PyTorch, tokenizers, evaluation suites, and utility packages that make data movement and model operations possible. Each pillar is an artifact with its own versioning, licensing, and vulnerabilities. Together, they form a triangle. Libraries shape how datasets are processed. Datasets shape what models learn. Models expose new demands that drive library updates. External tool integrations extend the chain beyond your repository. Modern systems frequently call out to search engines, code execution sandboxes, vector databases, document parsers, payment gateways, or enterprise software like customer relationship management and ticketing platforms. In retrieval-augmented generation, for instance, the quality of the answer hinges on connectors, parsers, and rankers that sit outside the core model. Keys, OAuth scopes, and network policies become part of your artifact story, because an attacker who controls a tool can steer or exfiltrate the model's outputs. Even simple utilities, like a PDF extractor or a Markdown renderer, can introduce subtle data shifts or injection vectors. Treat every integration as a dependency with a lifecycle, a maintainer, and a security posture. Your model doesn't just use tools, it inherits their strengths and their weaknesses. Risk propagation is the phenomenon where a small upstream defect becomes a large downstream incident. A mislabeled subset in a safety dataset can bias a classifier, which then misfilters training data, which then nudges a generative model toward undesirable outputs. A compromised package in a pre-processing pipeline can embed a backdoor that only triggers on special tokens, evading routine tests but manifesting in production. Even benign changes, like an updated tokenizer, can shift embeddings enough to degrade retrieval quality or invalidate cached indexes. Because artifacts are interdependent, risks are rarely isolated. They cascade across boundaries, multiplying impact. The practical lesson is to assume risks travel and to build circuit breakers, validation gates, canary evaluations, staged rollouts, and immediate rollback plans. If you can trace how information and code move, you can predict where faults will surface and how to contain them. Before we dive into controls, catalog the artifact types you'll manage. Training datasets include raw corpora, curated subsets, annotation guidelines, and label files. Each is a versioned asset. Pre-trained models span general-purpose foundations and domain-specific checkpoints that you load and adapt. Embeddings and indexes are the semantic memory of your system, produced by encoders and arranged by algorithms such as hierarchical, navigable small world, or inverted file product quantization. They behave like data products that must be reproducible. Deployment containers wrap runtimes, drivers, and system libraries into portable units that carry your model into staging and production. You can think of this as a model bill of materials, a structured inventory that names, versions, and signs each piece. With a clear inventory, supply chain security becomes concrete work, not an abstract aspiration. Open source is both a blessing and a risk. Community code accelerates innovation, fosters transparency, and enables small teams to achieve results once reserved for major research labs. Yet this openness creates risks, particularly when relying on unvetted contributors. Malicious package uploads have been documented across many ecosystems, and a single npm install or pip install can quietly introduce malware into a build. Rapid version changes in popular projects can outpace an organization's ability to validate, forcing teams into either stagnation or unsafe updates. Without clear ownership or strong provenance guarantees, open source becomes an implicit trust network. It's not about abandoning open source, but about adopting practices like curated mirrors, internal vetting, and contribution reviews that reduce exposure without losing its advantages. The same openness that fosters collaboration also widens the attack surface. Containers are another artifact type with unique security needs. A deployment container often bundles the model, runtime, drivers, and dependencies into a single package. This convenience also makes it a tempting target. Vulnerability scanning can reveal known flaws in system libraries or dependencies, while minimal runtime images reduce the attack surface by stripping unnecessary components. Signed build processes ensure that containers come from trusted sources and haven't been tampered with in transit. Continuous patching is especially vital, since container images often embed operating system layers that require frequent updates. A vulnerable container doesn't just threaten availability, it can open a door for attackers into the environment hosting the AI system. By treating containers as living artifacts that need ongoing care and verification, organizations prevent them from becoming static liabilities in an otherwise dynamic ecosystem. Dependency management is the glue that holds artifact security together. Version pinning fixes dependencies to known good versions, preventing surprise updates from breaking systems or introducing vulnerabilities. Using vetted repositories limits exposure to malicious uploads, while automatic updates with checks strike a balance between agility and safety. Separation of environments, such as keeping development, testing, and production isolated, helps ensure that experimental dependencies don't leak into critical deployments. Without disciplined dependency management, organizations risk creating a spaghetti graph of uncontrolled packages, each pulling in more hidden dependencies. That complexity magnifies attack surfaces and makes it nearly impossible to track what is truly running in production. In practice, good dependency hygiene is less about technology and more about discipline, setting policies, monitoring adherence, and embedding checks into every build process so unsafe components never make it to runtime. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Third-party vendor risks are often underestimated because many organizations assume that outsourcing a component means outsourcing its problems. In reality, vendors introduce new attack surfaces and legal exposures. Contractual gaps may leave ambiguity over who is responsible for patching or monitoring. Insufficient security audits mean you may never know how rigorously a provider protects their code or data pipelines. Weak provenance guarantees can obscure the true origin of supplied models or datasets. Over-reliance on providers creates single points of failure, making it difficult to pivot if something goes wrong. Evaluating third-party vendors through both legal and technical lenses ensures that you aren't blindly inheriting risks. By demanding transparency, regular audits, and clear accountability, you can make vendor relationships a strength rather than a vulnerability in your AI supply chain. License and legal risks are another dimension of supply chain security that go beyond technical vulnerabilities. Many pre-trained models are distributed under unclear or restrictive licenses, and using them without diligence can expose organizations to intellectual property disputes. Compliance obligations such as handling personally identifiable information under data protection laws may apply even if you didn't create the dataset. Redistribution limitations can affect your ability to share or sell products built on top of certain artifacts. These legal risks often surface late in projects, when models are ready to be commercialized, making them both costly and disruptive. Embedding legal review into the supply chain process ensures you respect intellectual property, avoid regulatory violations, and maintain the freedom to operate. Legal clarity transforms uncertainty into a predictable framework for innovation. Supply chain monitoring provides the visibility needed to spot emerging risks before they cause harm. Continuous artifact scanning allows you to detect vulnerabilities or unexpected changes in datasets, models, or containers. Anomaly detection in updates can reveal suspicious version bumps or unusual activity in repositories. Watch lists for dependencies highlight libraries with histories of compromise or abandonware, so they can be replaced proactively. Forensic traceability provides a detailed trail of what versions were used, when, and by whom, enabling investigations when something goes wrong. Monitoring isn't just a defensive tactic. It creates the feedback loops that make supply chain governance effective. When organizations see their supply chain clearly, they can act swiftly, surgically, and confidently, rather than stumbling in the dark after an incident has already spread downstream. Governance and accountability transform supply chain controls from best practices into enforceable standards. Clear ownership of supply chain security ensures that no critical artifact is left without oversight. Mandatory provenance checks, such as requiring signed attestations for datasets and containers, make security non-optional. Documentation of dependencies provides visibility into what your system actually uses, reducing the risk of shadow components slipping in unnoticed. Escalation procedures define how issues are raised and resolved, avoiding the paralysis that can follow when no one feels responsible. Governance frameworks anchor supply chain practices in policy, while accountability ensures that policies translate into consistent action. Together, they create the organizational discipline needed to turn scattered controls into a coherent defense. Automation of supply chain controls integrates these practices into the daily workflow. Continuous integration and deployment pipelines can enforce artifact verification automatically, refusing to build or deploy if signatures don't match. Artifact verification pipelines ensure that each dataset, model, or container passes checks before progressing to the next stage. Automatic rollback triggers provide resilience, allowing systems to revert quickly if an artifact is later found compromised. Audit-ready logs capture every verification, update, and rollback action, creating an evidence trail for both security teams and regulators. By automating controls, you remove the burden from individuals and ensure that protections are applied consistently at scale. Automation transforms supply chain security from an aspirational checklist into a lived reality embedded in the development process. Metrics for supply chain risk provide a way to measure progress and expose weaknesses. Tracking the number of dependencies highlights the complexity and potential attack surface of a system. Monitoring update frequency reveals which artifacts may be stale and accumulating vulnerabilities. Categorizing vulnerability severity helps prioritize patching efforts where they matter most. Measuring patching timeframes shows whether your team can respond quickly enough to emerging risks. These metrics not only provide situational awareness but also guide resource allocation and decision-making. A system with many unpatched high-severity vulnerabilities signals urgent intervention, while stable metrics show that governance is working. By quantifying risk, organizations can move beyond vague concerns and into structured, data-driven improvement of their AI supply chain security. Cloud provider considerations add another important layer to supply chain security. Many organizations rely heavily on managed services, whether for storage, compute, or model hosting. These services operate under a shared responsibility model. The provider secures the underlying infrastructure, while you remain accountable for the configurations and artifacts you supply. Trust in managed services is necessary but should never be blind. Attestation mechanisms, such as cryptographic proofs of runtime integrity, are increasingly offered by major cloud platforms and should be leveraged to validate that your workloads run on trusted hardware. Monitoring provider updates is also crucial because a single change in a managed runtime can cascade into unexpected behavior in your applications. Engaging with cloud providers as partners, demanding transparency, and understanding your slice of responsibility help ensure that cloud adoption strengthens rather than weakens your supply chain posture. The tooling ecosystem for supply chain security has matured rapidly, offering teams practical options for automation and assurance. Software composition analysis tools scan codebases and containers to identify known vulnerabilities and dependencies. Container security platforms integrate with registries and deployment pipelines to enforce scanning and signature verification. Dataset verification frameworks can check for consistency, labeling errors, or signs of tampering before training begins. Provenance record systems create tamper-evident logs of artifact history, making it possible to demonstrate compliance during audits. Choosing the right tools depends on your architecture and risk profile, but the broader point is clear. Relying on manual processes is no longer sufficient. Leveraging purpose-built tooling turns abstract best practices into continuous, repeatable checks that align with both security and operational needs. Resilience through redundancy recognizes that no single supply chain control is perfect. Maintaining multiple trusted sources for artifacts ensures that if one repository is compromised, you can switch to another with minimal disruption. Fallback mirrors help maintain availability when upstream services are down or under attack. Cross-validation of models from different sources can detect tampering or performance anomalies, providing confidence in integrity. Disaster recovery planning, including backups of datasets, models, and containers, ensures that you can restore functionality even after a catastrophic supply chain event. Redundancy is not about inefficiency. It's about creating safety nets that make your systems resilient against both deliberate attacks and accidental failures. By layering redundancy into the supply chain, organizations trade some simplicity for robustness, which is often the wiser long-term investment. The strategic importance of supply chain security in AI cannot be overstated. A compromised artifact doesn't just threaten a single deployment. It can undermine trust in an entire product line or even an organization's reputation. Preventing systemic compromise requires proactive controls and vigilance across every artifact and dependency. Maintaining trust in AI artifacts reassures stakeholders, users, customers, regulators that the system's behavior is authentic and reliable. Compliance with emerging regulations will increasingly depend on demonstrating provenance, integrity, and governance across the supply chain. Assurance for stakeholders, whether investors, partners, or end users, rests on confidence that the AI system has not been tampered with. Treating supply chain security as strategic rather than tactical elevates it from a technical detail to a board-level concern, influencing how organizations allocate resources and design long-term architectures. In conclusion, the AI supply chain is as critical as the models themselves. Every dataset, library, container, and integration represents a potential entry point for risk. By applying artifact integrity controls, enforcing governance, and leveraging automation, organizations can transform a fragile, sprawling supply chain into a secure, transparent, and resilient backbone for AI systems. Monitoring and metrics provide visibility, while redundancy ensures resilience against inevitable disruptions. Legal and vendor considerations highlight that risk is not only technical but also contractual and regulatory. Ultimately, secure supply chains uphold trust. Trust in models to perform reliably, trust in organizations to safeguard stakeholders, and trust in AI as a field to advance responsibly. As we turn to the topic of secure fine-tuning in the next episode, we carry forward the principle that every artifact tells a story, and it's our responsibility to ensure that story is trustworthy. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.